Now there's several different ways in which we can relate force and motion, but as I said in the previous video, we're going to start out these next few weeks focusing on Newton's second law. And with that, we're going to be able to, again, describe the relationship between force and motion. Again, we know how to, or should know how to describe forces acting upon a body from statics, and motion we've covered in this class for the past few weeks. And so we're going to use this relationship, and then ultimately what we're going to produce are equations of motion. So equations that describe the motion of a system that also consider the forces that generate that motion. And so what is Newton's second law? Newton's second law states that the rate of change of the momentum of a body is directly proportional to the force applied to it. And this week, we're going to focus specifically on linear momentum. And very shortly, I'll show how that relates to force applied. And so we'll write out this equation here, and we're going to then use that equation and that relationship to just go ahead and start calculating those equations of motion. Let's first define linear momentum for a particle. So the linear momentum for a particle at point P with respect to frame A. Well, first of all, it's written using the following notation. So we use a lowercase p to indicate linear momentum, even though there is no p in linear momentum. It just is what it is. All right, so we got our lowercase p for linear momentum, and that's the linear momentum of point P, the particle at point P in frame A. And that is equal to the mass of the particle times its velocity in frame A. And so right here, this is our definition of linear momentum for a particle. And so if you go back to Newton's second law, what it's saying is that the rate of change of linear momentum, which we write as, sorry, no equal sign there. The rate of change of linear momentum is directly proportional to the forces applied to that particle. And so we write force as a vector quantity here. Force doesn't get a little letter up at the top, and that's because it's written with respect to a fixed frame, but it doesn't actually matter what that fixed frame is. Okay, so this is Newton's second law. And so from that, right, we can plug in our equation up here. So we can now rewrite this as force is equal to the time derivative of mass times velocity. Now, most of the time, not always, but most of the time, we can consider mass to be a constant. And so unless you are told otherwise, we can assume mass is constant, so we can pull that out. Examples of systems where mass is not constant, for that you should probably refer to the rocket team, right? So something that might like utilize fuel over time. So your car or an airplane. Now, of course, depending on the time scale of the motion that you're looking at, it may or may not matter. But it's true that mass does not have to remain constant. But again, for this class, pretty much always going to be constant. So now we can write this here, and as you, I'm sure you all recall, this term here leads us to write that forces equal to the mass times the acceleration of point P in frame A. And so this is where the famous F equal ma equation comes from. And when you look at this equation, it should be clear that on one side you have force, and on the other side you have motion, right? This acceleration term. And so again, for the next few weeks, this is one of the equations that we're going to use in order to relate force and motion and ultimately get to, we're basically going to plug in the force vector. So for a given particle, plug in the force vector, plug in the acceleration vector, and that will give you your equation of motion. And so we'll go through that in the next few videos, some example problems. But one thing I do want to note is a consequence of this equation is that so let's say if we set the force equal to 0, so nothing, you imagine you have a closed system, nothing, no external forces are being applied. What that means is that, if you come back over here, what it's saying is that the change in linear momentum, angular momentum's next week, so linear momentum is going to equal 0. So it's going to remain constant. So if you don't have external forces, linear momentum is constant. And so we say that linear momentum is a conserved quantity. And this is conservation of linear momentum. All right, so now we'll move forward with, and we're going to actually use this equation here to relate our forces of motion and get our first equation of motion.